This is the story of what's called the observable universe. Hi, my name's Alex. I've argued enough for a lifetime. If you'd like to know more about nature, how we find out about it, and how all of this relates back to being kind in our daily lives, please consider subscribing, hitting the bell, and sharing. I can't promise that you'll find answers in single videos, but it's all there, in the channel as a whole. Onto the center of the universe. We can start out with a word that really is two words, only it's not. You have probably already heard it often enough. Light year, as in Buzz Lightyear. What is a light year? Even, or perhaps especially if you are one of those thinking, boring, please make yourself conscious of this little factoid. 1 light year equals 946052840000000 meters. That's 9 quadrillion, a number with 15 zeros, and then some. Sure, go ahead and think that you know this already, and then I'll ask you to describe that number in a meaningful way. Because let's be honest, distance between stars, quote-unquote, for example, doesn't mean anything to any of us on our little planet. Don't flatter yourself, it really doesn't. It's about as much as I can do, at any rate, to imagine Earth. It took us quite a while to get to the point where we can look at images from space and imagine it properly. After this one, go listen to Imagination and Mathematics. That history is quite the doozy too, full of logical and beautiful thought within an ever-expanding framework of knowledge. It took us a really long time to imagine Earth properly. People deride Ptolemy, for example, for thinking of Earth as the center of the universe. Well, he arrived at this conclusion not out of stupidity, but, well, again, head on over to the other video. Here, the idea is rather simple. Earth is small, very small, not even just in the context of the universe as a whole. No, we can stay in our little corner of the Milky Way galaxy, the solar system. We have serious problems imagining just the simplest of things about the solar system. See, we can very easily imagine how big the planets are relative to each other and to the Sun. Chances are you have seen oodles of images already comparing balls of different sizes. Jupiter, for example, is the biggest planet with its 140,000 kilometers in diameter. It dwarfs poor Mercury, which is smaller than our own moon. Then, Jupiter is itself just, well, minuscule compared to the Sun with its 1.5 million kilometers in diameter. Then, there are the distances. I mean, looking at how we are taught about the solar system, you'd think those planets align in a straight line, orbiting together around the Sun. The distances between them more or less equal at all times, yet they don't, like at all. And the orbits themselves, that is, the fictitious lines the planets follow around the Sun, have distances to each other that are too vast to comprehend. The images we see online or in the classroom or on TV or wherever are ingrained in our brains, it seems, for the reality is right there in front of our eyes. If you want to get a sense of just how far away the other planets are, look up. Mercury is on average closest to Earth and, if you live in one of the metropoles, quite invisible to you. At any rate, if you have nothing more than your eyes to look with, it's simply a point you may or may not see up there. One of the stars, same with Jupiter. As big as it is, it still looks like one of the stars. Same with Venus, Saturn, and all the others. Either you can't see them at all, or they look like just another star. Brighter in some cases perhaps, but nonetheless just a star. By the way, if, quote, Mercury is the closest planet to us, quote end, irks you a little, feel free to investigate. One tip to avoid frustration with either me or yourself is to be conscious of what I just said. Closest orbits is different from closest on average. Anyway, if you ponder it all for a second, do you understand that this means that the planets are very far away indeed from Earth? Still, I don't blame you, or myself for that matter. We need to visualize all of it somehow, and there's gonna be cuts made. Just keep it all in mind when you hear Neil deGrasse Tyson or any one of those guys talk about the solar system as our cosmic neighborhood. because they're right too, in the grand scheme of things, those humongous distances between the planets that make Mars and Jupiter look small aren't all that big, like, at all. The Milky Way is around 100 light years in diameter. There's more than 400 billion stars in it, and all of them are much, and I mean much, much further away from each other than we are from, say, Pluto, which isn't a planet. Sorry. So, the Milky Way is a so-called spiral galaxy with a big fat center in the center and things that look like arms spiraling around it. Only when you look at the whole spectrum of light, you'll find that there are no arms. There's just a disk, which isn't a disk since every point of light you may imagine right now is just so far away from each other point of light, a sort of light dusting of star systems. Got that? Honestly, it's a little whatever already, because we can't imagine it anymore. Our solar system resides somewhere a little to the outside within what looks like one of the arms in the light we can see with our own eyes. And we know that, despite never having been outside our galaxy to take a look. Here, shall we go even further? There's more galaxies out there than there are grains of sand on Earth, we think. The number might be high enough to be compared to something else rather. I don't know. What do we humans do when faced with something so utterly gigantic and beyond our reach? We categorize the hell out of it. Paper size or planet. Garbage cans or galaxies. We categorize. 'Cause nothing says, I have control, more than slapping some good old made-up names on something. Here goes. There's the ones everyone knows. Spiral galaxies. Only there's already two types of those, one which is a true spiral and one with a sort of bar of stars in the center. Then there are elliptical galaxies, which is funny because galaxies are three-dimensional things while ellipses aren't. Of course, there's always stuff that doesn't fit anything. They're called irregular galaxies. But make no mistake, a galaxy that sort of has a bar in the middle, but not quite either, perhaps because it just looks different at different wavelengths or for other reasons. If they should but don't quite fit the categorization, then they're not irregular, quote-unquote. At all, actually. Irregular galaxies don't fit in a certain way. And no, I haven't quite understood that either. On top of that, you probably know the guy who came up with these categories. Edwin Hubble. He of two telescopes that weren't his. But that's a different story for a different day. For now, just think about it for a second. Those little creatures on their little planet in a solar system on the outskirts of some galaxy have the guts to categorize galaxies. And doing a really poor job at it too. I mean, we named our own galaxy with its 400 billion stars after the milk of a Greek goddess. At least in English we did. But, you say, surely we aren't that little, like it all, and stuff, right? Well, I'll put that famous Voyager image on screen now. Earth seen from Saturn, from well within the solar system, that is. Not far out at all, actually. If you know it, you know what's coming too, so don't bother sitting up and looking at your screen. Just keep sitting back and relax. If you don't, have a look. Earth is that dot right there in one of the beams of light reflecting from the Voyager satellite. Yes, that right there. Here's what Carl Sagan had to say about this image. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings. how eager they are to kill one another, how fervent their hatreds. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. This quote never gets old. It never gets irrelevant, it seems. But that's the thing, of course. We dare to categorize galaxies. That's what we do. And for a good reason too, since it helps us understand the universe around us and, ironically, our small place in it. We do so by some of the largest machines ever built. These are telescopes, put on the ground, following with the Earth's rotation to observe the part of the sky visible to that particular spot on our planet. They are huge for a reason, because the larger you build them, the more precise the observation could be, if there wasn't an atmosphere screwing it all up. Have you ever seen the air cooking over warm asphalt on a hot summer day? Yeah, that's it. That's the effect those telescopes with their sensitive instrumentation and mirrors see every day, every night, all the time. The effect is always there, you see, because the Earth is warmer than 0 degrees Kelvin. So mostly those telescopes are built on mountaintops. There's less atmosphere above them there, and thus less disturbance. Wouldn't it be awesome if we could build a telescope in space, that is, outside the Earth's atmosphere? Truth is, we do that already. You've heard about the Hubble telescope, surely. It's been launched in the 90s and is still going strong. There's oodles of solar telescopes too. They observe the one star in our vicinity, if you can call a distance of 150 million kilometers in the vicinity. Mostly, however, satellites observe the deep sky and do so without the distractions of the atmosphere. They're not big though. They can't be. They're satellites. They're launched into space by rockets. They can turn to look at all the sky, but they can't be big. I'm not obsessing over numbers generally, despite that little light year game in the beginning there. If you are, though, just go and check out the sizes of both land-based and orbital telescopes. Take a look at the James Webb telescope in particular. It's the size of a tennis court, roughly, but it's light for a tennis court. And well, if you don't know, just check out how they fit a tennis court into a rocket. You won't be disappointed. We're an awesome species who are able to build any one of these things, is what I'm saying. I mean, there is a whole army of these satellites in space, with a whole infantry of larger telescopes on ground to boot. How, well, awesome is that, in all senses of the word? Okay, enough about telescopes. Let's get back on track. What does observable universe really mean? You know that I like it when you don't have to be a genius to understand something, because the clue lies in the word. I'll show you how to take the word observable and deduce a few things from it. Observable. We are able to observe whatever is observable. Talking about the observable universe then means that there is a part of it we can observe. It may be the whole universe, but we think it isn't. Don't ask me why. That's the complex stuff again, and there are others who are better at explaining it on YouTube. But here we are. We see part of the universe. And when I say see, I don't mean the part that you can see when looking up. That's the visible universe. And that's different at basically every place on Earth. So how big is that observable part of the universe? Well, we can tell now, can we? We talked about what a light year is in the beginning. The universe is a little under 14 billion years old, so the observable universe is a little bit under 14 billion light years in radius all the way around us, right? Wrong. Let's be honest. The universe expanding is a mind-boggling concept. Let's just accept it and move on. Except we can't, because this expansion explains why the observable universe is more like 40 plus light years across. The farthest galaxies sent their light towards us billions of years ago, when they were billions of light years closer to us. Yes, that is a sentence which will incite questions in the observant observer. Write them down in the comments if you will, and let's talk. If not, that's okay too. For now, let me just tell you that Einstein's genius, for example, doesn't lie in the maths or any of the other typical genius things about physics that we normally think about when thinking Einstein. He needed help, and a lot of it too, for that stuff. No, his genius was in seeing the connections and then not being so full of himself as to not ask for help. Google Einstein and Hilbert and take it from there. These theories of relativity of Einstein's, to which I am alluding by saying all of this, were collaborations built on the knowledge that came before them. Where did we hear that before? Ah, yes, science. That's just how it works. You may know about Ampère and Gauss and those guys from physics or technology class in school. Those were the geniuses of the 19th century. Their Einstein was called Maxwell. Maxwell was an eccentric fellow playing around with wood. Not a genius, necessarily. But he did put everything together into Maxwell's equations and gave us a comprehensive way of treating electricity and magnetism. Along comes the actual Einstein and finds these equations to not be fully explored, and off we go towards light being bent by stars and a completely new understanding of the universe. I mean it. The expansion of the universe is something the Big Bang Theory predicts. That theory is a result of Einstein's work, not found by him, but found in his work. You see, if you try to solve Einstein's equations, you'll find that you can't. They're coupled, intertwined with each other, the numbers moving around each other like drunken Morris dancers. Yet you can estimate certain situations. You can, for example, assume the mass of an object to be so high as to think that its mass density, that is, how tightly it is packed, to approach infinity. Once you do that, you can do maths and find that there could be stars out there whose gravitational force is so high that even light can't escape. There are stars like that. They're called black holes. Another one of these assumptions is then connected to the beginning of it all. In physics, the beginning is often connected to the time variable being equal to 0, or at the very least being very, very small. Assuming the time variable in these equations to be small leads to another revelation. The whole universe may have just been concentrated in one particular point, only at the start of it all, and only for the tiniest of fractions of a second. The idea was derided thoroughly when it came up. Big Bang is an expression that doesn't describe what happens very well. Rather, it describes the emotions of disgruntled and somewhat disbelieving colleagues of those who saw it all in Einstein's equations. It, like the expression black hole, is an insult. This is science, though, and the argument gave place to reality eventually. The reality was that there were strong indications for the Big Bang to not be wrong. For one, light emitted by the stars wasn't quite what it was supposed to be. Hubble himself, the person I mean now, saw already in the 1920s that all light reaching us was shifted towards longer wavelengths, that is, red-shifted, quote-unquote. That's what that word means. Think of a car driving away from you. The motor sound deepens, that is, the wavelength of the sound increases. When we see the wavelength of star and galaxy light increasing, we know that they move away from us. And so they do, as the Big Bang Theory predicts. Keep that in mind, we'll come back to it in a second. First though, there's a really and utterly impressive feat of prediction which validated the idea of a Big Bang probably more than anything else. Radiostatics. I will admit that you may have heard this before. In that case, remind yourself of the fact. If not, well, what if I told you that the only thing you need in order to hear, and I mean literally hear, the echoes of that Big Bang is an old-fashioned radio receiver? About 1% of the static you receive is what's called cosmic background radiation. In that beginning I talked about, all, and I mean all of the energy in the universe was supposed to be in one point. At that point, as it were, all bets were off. But there was an underlying process which simply had to happen in order to come to where we are today. See, when that point became just a little bigger, just enough to actually be of any dimension at all, there is one and only one form of energy possible. That's radiation. Nothing else, just radiation at the highest frequency possible. Then the universe expanded, the energy spread out and became cooler at any one place, even though the total energy in the universe didn't change. Cooler just meant radiation at lower frequencies in the beginning. Yet eventually, as the universe just got bigger and bigger, that is, cooler and cooler at any one place, it was possible for matter to be created out of the radiation. Think water becoming ice at a particular temperature. In the same way, hydrogen started existing simply because it could. Not all radiation became hydrogen though, but the universe got transparent, as they say. The radiation could start to travel long distances through space filled with hydrogen and, with time, more and more nothing too. In other words, radiation that survived this transition could make its way deep into the universe and, in principle, be observed a couple of billion years later by some nun-monkey on a planet in the outskirts of a barred spiral galaxy. That's us. I mean, us. And we could observe it. In the 1970s or 1980s, I don't quite remember now, the first satellite to measure this radio static a little more precisely was launched into orbit and, lo and behold, could precisely match the radiation to the prediction of the Big Bang Theory. How cool is that, huh? It's important to note, however, that not every esoteric idea based on a few data points a couple of decades earlier means that you have found the key to the meaning of existence or any such thing. As it is, we still don't actually know whether the Big Bang Theory is really describing nature all that well. There's things about it which vex some scientists. Did I really just have to make myself read that combination of words? Anyway, this is why a lot of us would like to have a different theory. I mean, it's not like any of what I'll say now disproves the Big Bang Theory or that nature does have to make sense to us even. But you know there's limits for everything, unless the universe is infinite, which it just might be. Well, you'll see what I mean in the proverbial jiffy. As Sean Carroll put it once, quote, "The beginning of the universe? No. It is the end of our understanding," quote end. It refers to the Big Bang itself here. T equals 0, the very start of it all. The problem is that we don't really know whether general relativity is valid then. Einstein's equations descend into what's called singularities. That's fancy speak for we have no way of knowing what happens. In this case, at least. What's a little bit, funny in fact, is that it doesn't really matter what happened at t equals 0 for the Big Bang Theory to be right, whatever that really means. The moment the time t is no longer 0, we do know what happens. We can calculate that. And those calculations show us a universe that is expanding much slower than we observe. In order to explain this, dark matter and dark energy are postulated. Dark means that we can't see them by any means, almost by definition. That's okay, you say. Black holes are like that and we found ways to detect and even image them, so what's the big deal? Well, 95% of the whole universe is supposed to be dark matter or dark energy. 95%. It's one thing that nature doesn't have to make sense to us. Of course it doesn't, but 95%? That number makes people rather nervous. Still, most people accept the existence of dark energy and started looking for it even. Truth is, I'd like for this part of this piece to be outdated before I finish editing the video. But at the moment we don't know what dark energy and dark matter could be. We have ideas, but we're not at the point of measuring or being able to induce the invisible, as in the case of black holes. And if you do want to find out more, I'll leave a link to a couple of great videos from Veritasium, SciShow and the like. They do a great job of explaining the details. I'm more into the perspective this can give us. Is there really a chance that this piece will become outdated at publication? No, not really. And that's saying something too, since in my life, like with a job and a family and so forth, a piece like this is planned a year before, written a month later, edited half a year later at least, and then recorded a couple of weeks before publication. Still, science doesn't move that fast. It moves in increments. I've explained that in multiple of the other videos, so check one out at random. The ideas are different. What takes time is sieving out the good ideas, the few good ideas. Scientists have a lot of ideas that don't make it through the sieve. Strangely, that can be a problem. Journalists love the ideas, especially the strangest ones. They meet a scientist who, through them, gets reinforcement for her strange idea and explains it enthusiastically. Then she reads the magazine or watches the TV or whatever and gets a slight shock. The keywords "scientists say" and some idea presented as fact. And off we go into discussions about climate change and aliens. Do you think this is not real? Well, what if I told you that millions of tourists travel to northern Norway to see the northern lights in mid-summer? What if I told you that at least one of them did so after reading an article in the German paper Frankfurter Rundschau? What if I told you that I know the scientist interviewed for that article? Sorry about that. It was probably not necessary to express myself in that way. The journalist was not just nice, but honestly interested when she visited us up north. She also had a job to do. In many ways, I simply don't envy her at all for that job. When talking aurora, you have to talk particle physics. That is, quantum physics. You have to. Most people don't, and just brush over that word there, particle, like it was simply clear what it stood for. I think she did a decent job, all things considered, but the misunderstandings remain. Particle physics, multiverses, string theories, Big Bang and whatnot. None of these make sense to us humans. It doesn't have to either. We're just that tiny little species on that mote of dust, as Carl Sagan called Earth. And yet, if you think about it for a second, there's no denying this little factoid. You are, and will be for the rest of your life, the center of your very own observable universe.